Right, so the question asks, what is the maximum and minimum amount of energy an asteroid can have during a completely inelastic collision with the Earth? So we know we have an asteroid called TBT or TB145. We want to find the maximum energy and the minimum energy for a completely inelastic collision. So we'll begin by kind of actually saying what we want to find. We want to find the kinetic energy for the asteroid. So we'll say Ke asteroid. And of course that's 1/2 mv squared. So that's the central equation we're trying to solve for. Now we'll have two different paths. There's Ke. Okay, so Ke minimum, we'll denote like that. It'll be 1/2 the lowest mass and the lowest velocity squared. And then we'll have another situation, Ke max, where we consider the 1/2 and the maximum mass the asteroid can be, and the maximum velocity squared. So what does that actually mean? The arrows, the maximum and minimum. What does that mean? Well, here, if we read the problem, we know we have an asteroid of a fixed diameter, and then of course the sun. It has a speed relative to the sun. That's constant, so there's no acceleration. But we know that the density of the asteroid can differ. But we also know everything else stays constant. So the radius of the Earth and its period stays the same. So what this means for us is that we could have a whole array of possibilities because of the density. If the density changes, so does the mass of the asteroid. So we can consider the minimum values for all of them, the minimum values for all of our variables, and also the maximum. So how does it actually work? We'll begin with central equation again. We want to begin by finding the mass. We'll do that in inch. So we know that the density is mass over volume. Now we also know the volume of a sphere is 4/3 pi r cubed. So let's write that down. The mass over 4/3 pi r cubed is the volume of a sphere. And then this is the mass of the asteroid, and this is the density of the asteroid. There. So that means if you want the mass of the asteroid, this would be just 4/3 pi r cubed, and then the maximum or minimum density. So we'll keep that like that. And then we'll rewrite these equations again. So this is then 1/2 4/3, times 4/3 pi, and of course the maximum radius cubed times the maximum, we're considering the minimum here in blue, times the minimum density. And of course the minimum velocity squared. And this would be our minimum kinetic energy. Of course we could do subscripts, but I think this notation is a bit easier to understand. We can also write this. So the maximum kinetic energy would be 1/2 4/3 pi, of course the maximum radius cubed, and of course the maximum density times the maximum velocity. Alright, now we move on to finding the velocity of the actual object. So here, we have both situations, the speed relative to the sun. So we know here that both of these speeds are relative to the sun, and that the Earth also has some velocity. So let's write that down. So we know that the velocity we're actually getting, you can write this in red actually. Velocity we're getting is going to be relative, so v relative. And so this would be either the sum or difference of both velocities. So plus or minus the velocity of the Earth and the asteroid. So what does that mean? Well, let's say we'll create an image. We have the sun, the asteroid, and then the Earth. Now, in a ideal, or not ideal, but the maximum dangerous situation, our Earth is doing its kind of rotation, and at the same time, our asteroid is going to hit the Earth. So at this point, this collision here, this velocity collision, we'll say, is the velocity of the asteroid plus the velocity of the Earth. But let's say in an unideal situation, they're kind of going opposite directions. That would mean that we collide with the Earth at a difference. So to show that, we could say it's going to hit the Earth sort of just straight on. So this would mean that we have a difference. So the velocity collision is going to be velocity of the asteroid minus the velocity of the Earth. So this is where it differs. And then we can extend on this more. Now, we know the velocity of the asteroid for both instances relative to the Sun, but we don't know the velocity of the Earth. But we're given enough information to figure it out. Alright, so now we have another step. So the velocity of the Earth would be, of course, distance over time, right? Now, what distance does it travel? Well, this would be the same as 2 pi r of the Earth over its period. So here we have that the Earth orbits a perfect circle of radius 150 times 10 to the 6 kilometers. So this would be the radius of the orbit, and this will be the period. So here, of course, the period is in days, but we want to be in SI units. So, of course, this would be ideally meters per second. So for us to do that, we'd say T times 364.25. Sorry, so it's already in days. So it'd be times 24 hours times 3,600 seconds. And the top is already in kilometers. So to convert that to meters, we just multiply by 1,000. Alright, and from there we get the velocity of the Earth. Meters per second. So that means the velocity relative would be the velocity of the asteroid plus or minus, whether you're considering the maximum or minimum, 2 pi, or we'll say actually 2,000 pi radius of orbit over, we'll do that part too. So 24 times 3,600 would be 86400. Of course, we can get rid of 2 zeros here. Pi radius of the orbit, 864T. And then we say the period of the Earth. So then we can plug that back in. So again, the minimum kinetic energy it can have would be 1/2. It'd be 4/3 pi. And of course we can say the minimum radius, but the diameter, and thus the radius of the asteroid, stays the same. So we can just say r asteroid cubed. But of course we need to consider the lowest density, since again it's saying that it ranges between two boundaries. So the lowest density times here would be considering the lowest velocity. So here would be velocity of the asteroid minus, in the worst case, or I guess the best case for Earth, they would be unaligned, so their velocities wouldn't add up. v minus 20 pi radius of the orbit, which stays the same, and 864, that period stays the same. So we no longer need the arrows to denote that it's the minimum, because we have the subtraction here, which already tells us it's the minimum. And then for the green, so the maximum kinetic energy you could have is nearly the same. So 1/2 4/3 pi r asteroid cubed, the maximum density times the velocity of the asteroid plus 20 pi radius of orbit over 864 period of the Earth. And then from here, you just have to plug in values. Now what you have to remember is that the density will change depending on whether you're considering the maximum or minimum situation. So here in the minimum situation, you would consider the lowest density that the asteroid could have. So here, that would be 2 grams per centimeter cubed. Here, this would be the maximum, or sorry, other way around. This is considering minimum. This is maximum. Right? And just another conversion. Our densities are in grams per centimeters cubed, but we always want it to be in SI. So then this would be, of course, for every 1,000 grams, there's 1 kilogram. So those cancel out. And then, of course, for every 100 centimeters, there's a meter. So then we can cube that. So let us get rid of these. So we can kind of expand that out. This will be 100 cubed centimeters cubed over, of course, meters cubed. Alright, so we get that the final conversion is 100 cubed over 1,000, which would be 100 cubed over 1,000, just 1,000. So times 1,000. So I'll rewrite this one more time. I'll actually just copy it. Alright, so here it would be lowest density. Density, we'll say low. This would be density high. Cool, and then of course we'd multiply by 1,000 for both. For the conversion factor. And then finally, one last thing. It wants us to state the answer to the nearest megaton, which is the same as 4.184 times 10 to the 15 joules. So we'll do one last conversion here. We will do in gray. This would all be divided by 4.184 times 10 to the 15. And of course, the same goes for the other one. There you go. And then you can sub in values. So we can try that actually. See if we get reasonable numbers. Of course, you could have plugged in values at any point. It's just good to get a final equation and then from there, type in everything. So over here, we get that 1/2, and then 4/3 pi. And the radius of the asteroid in the minimum was 500/2. So this was 500 over 2 cubed, and the lowest density was 2. Of course, that's 2 times 1,000 for the conversion to kilograms per meter cubed. And then also times the velocity, so 36 minus, it would be 20 pi. The radius was 150 times 10 to the 6, I think. Is that what it was? 150 10 to the 6 kilometers per hour over, of course, 864. The period was 364.25 days. And of course, all of that divided by the conversion to megatons of TNT. Over 4.184 times 10 to the 15. This isn't straight. There we go. Now for the maximum value, we would get that this is equal to 1/2 4 over 3 pi. The radius for this one was 350. 350 over 2 cubed. The highest density, which I think was 5. Yeah, 5. And of course times 1,000 for the conversion rate to SI units. It's always recommended to convert to SI, regardless of course, if you're better at handling the variables and the units, go ahead. Converting to SI will always give you back SI units, and so from there you can do more conversions instead of doing everything in between and risking making a mistake. So this would be 31 plus 20 pi. The radius was over 864. 5.2425 4 days. And then, of course, the conversion factor to megatons of TNT. 4.84 times 10 to the 15. Now, I'm going to put this in a calculator. Okay, let's see. Let's put this into Esmos Scientific. Times 4 over 3 pi times 500 over 2 to the power of 3 times 2 times 1,000 times 36 minus 2 pi 150 times 10 to the 6 divided by, we'll do the full conversion thing actually. So we'll do 24 times 3,600 times 364.25. And then of course, all of this divided by 4.184 times 10 to the 15. Okay, something went wrong. It's a very small number. Let's see what happened. course, this is the minimum. So let's see what I got before. This is the maximum. Okay, I guess that's just that small. Well, of course, that's a lot actually. Not gonna be. It's still megatons of TNT. All right, that's the first one. Now for the lowest, we're gonna change some things. So here would be, or sorry, the highest right now, 350, 5, 36 plus. Let's see here. So it's still a pretty small number. That's still a pretty small number. Let's see. What's a position of nearest megaton? Yeah, that's not working, huh? Let's see where I went wrong. Oh, yes. Okay, I didn't convert this. That's why. So this was in. Let's see here. Oops, wrong question. So this was in kilometers per second. There you go. So this should be 1,000 times 1,000 times 1,000. Okay. Still doesn't make sense. Oh. So they would round to just 1. Uh, and let's see here. Do we want kilometers per second or? Okay, this would give us. Yes. So this is kilometers. So of course we would multiply this by 1,000 to give us meters. And this bottom part would be seconds, meters per second. So for us here, it's giving us a smaller number. Interesting. What happened here? It's probably the minimum, which was green, or sorry, blue. I mixed up the signs. So we chose the minimum or smallest density, 2 grams per centimeter cubed, 500 meters over 2 cubed, which would be meters cubed, kilometers per second multiplied by 1,000. Once we multiply this, 2 pi r. This 2 pi r is, of course, the circumference. Is 2 pi r, yeah. Pi r cubed. Okay, okay. I didn't square the velocity. That's why. So again, it's 1/2 mv squared. So our entire velocity term should be squared. That's why. That's why it's so insanely low. This move from there to there. Oops. Okay, so this would be there to there. Right. So square that. There you go. That makes more sense. All right. Square that. There you go. Now that makes sense. So what we were forgetting is our square, or the 1/2 mv squared. There you go. And there you go. So yeah, that should be your final answer. This is the minimum, and that's the maximum energy that both of these collisions could have.